Let me adjust the headline before we start, because precision matters here. 6G is not deployed. It does not exist as a commercial service in any country on Earth as of 2026. The first commercial 6G rollouts are targeted for roughly 2028 to 2030 depending on region, with the initial full specification expected from 3GPP in Release 21, following the preparatory work happening in Release 19 and 20 right now. The claim that 6G is already here is, in the commercial sense, not true, but the research is here. The standards drafts are here. The test beds are here. The capability that has people worried, the ability of a cellular network to sense the physical environment independent of any device being carried, is being actively engineered in full public view, and understanding what is actually being built is the difference between informed concern and unfocused fear. Let me show you what is actually happening. The capability in question has a name. Integrated Sensing and Communication, abbreviated ISAC, sometimes called Joint Communication and Sensing, JCAS in the European research literature. The premise is elegant in an engineering sense and consequential in a privacy sense. A cellular base station, in normal operation, emits radio frequency signals that propagate through its coverage area. Those signals reflect off anything in the environment: buildings, vehicles, people, vegetation, weather phenomena. Conventional cellular networks ignored the reflections. They were noise to be filtered out. ISAC is the engineering discipline of not ignoring them. It takes the same signals that a base station is transmitting for communication and processes. The reflections as if the base station were a radar. This is not a metaphor. The mathematics of cellular signal propagation and the mathematics of radar are closely related. Both rely on the timing, the amplitude, and the Doppler shift of received signals to infer the position and motion of reflecting objects. The difference historically has been that radar systems were purpose-built for sensing, while cellular systems were purpose-built for communication. Integrated sensing means building systems that do both simultaneously, sharing the same spectrum, the same antennas, and in many cases the same waveform. Why is this becoming possible now? Several technical trends converge. First, the higher frequency bands that 5G already uses, millimeter wave, roughly 24 to 100 gigahertz, and the even higher bands that 6G is expected to use, sub-terahertz, 100 to 300 gigahertz, offer the wavelengths necessary for meaningful spatial resolution. At these frequencies, reflections from human-sized objects carry distinguishable signatures. Second, massive MIMO antenna arrays, multiple input, multiple output configurations with dozens or hundreds of antenna elements, allow base stations to form narrow directional beams and process reflected signals with the directional precision that sensing requires. Third, the computational capability at the base station has grown enough to handle the signal processing workload of radar-grade analysis in real time. Fourth, the standard's Body 3GPP has opened formal work items to specify how ISAC will be integrated into the cellular protocol stack, ensuring that sensing does not break communication and that multi-vendor interoperability remains. The standardization work is public. 3GPP Release 19, frozen in 2025, introduced the initial sensing study items for 5G Advanced. Release 20 is scoped to expand the sensing framework. Release 21, expected to land in 2028 to 2029, is where the first full 6G specifications including ISAC are expected to mature. The timelines slip, release numbers shift, but the direction of travel is clear. You can read the technical reports. You can attend the public workshops. You can follow the research papers from groups at Nokia Bell Labs in Finland, Ericsson in Sweden, Huawei in China, Samsung in South Korea, and university research groups across Europe, North America, and Asia. This is not speculation. This is a visible, well-funded, multi-year engineering program. What specifically is ISAC expected to be able to do? At the basic level, detect the presence of objects within the coverage area of a base station, distinguishing stationary from moving objects. This sounds benign. It is the foundation of a lot of useful applications. Traffic monitoring without cameras, smart building occupancy. For HVAC efficiency, fall detection for elderly care, Wildlife monitoring. At intermediate resolution, estimate the position and velocity of detected objects with precision suitable for tracking moving targets. This resolution is expected to improve as frequency bands rise and antenna arrays densify. The research demonstrations have shown meter-level position accuracy in outdoor environments and sub-meter accuracy in controlled indoor environments. This is sufficient to track the path of a pedestrian through a coverage area. At higher resolution, classify the type of object based on the characteristic radar signatures of its reflections. The way a human's radar return differs from a bicycle's from a vehicle's. Micro-Doppler signatures, generated by the periodic motion of a walker's limbs, allow human motion to be identified, and in some experimental work distinguished at the individual level based on gait patterns, though this latter capability is more research than deployment. At the most ambitious resolution, some research groups have demonstrated through-wall sensing, gesture recognition, and even coarse vital sign estimation, heart rate and breathing rate detected from subtle chest wall motions, using radar techniques at cellular adjacent frequencies. Whether these capabilities become part of commercial ISAC deployments or remain in the research tier is an open question, but the engineering path is known. Now the privacy implications. A cellular base station that can detect the presence, location, and movement of pedestrians within its coverage area is doing something qualitatively different from what any previous cellular generation did. Previous generations tracked devices. ISAC, in its fullest form, can sense the physical environment itself. The tracked subject need not be carrying a phone. The tracked subject need not have any relationship with the network operator. The tracked subject may not be aware that sensing is occurring. The tracked subject cannot opt out by turning off a device, because there is no device under their control that the sensing depends on. This is the part that genuinely warrants attention, and it is the part that is still being decided. The standards bodies are not ignoring it. ETSI and 3GPP working groups have included privacy discussions in the ISAC workstreams. The question of what consent framework applies to environmental sensing, who owns the sensor data, what purposes the data can be used for, and how long it can be retained is being debated. The outcomes of those debates will shape what ISAC actually looks like when it enters commercial deployment. They are not predetermined. Compare ISAC to existing technologies that raise similar questions, because the comparison helps calibrate the concern. Public closed-circuit television cameras already perform a function adjacent to ISAC. They sense the presence and movement of people through public spaces. They are more precise in some ways, less precise in others. They are governed by a patchwork of regulations that vary enormously across jurisdictions. Millimeter wave body scanners at airports, automotive radar in new cars, Wi-Fi-based motion sensing that has been deployed in some smart home products. All of these are sensing technologies with overlapping capabilities. ISAC is not a qualitatively new category of surveillance. It is a new deployment medium for a family of sensing techniques that have been emerging across multiple domains. The significant difference is scale. Cellular infrastructure is ubiquitous in a way that CCTV is not. If every cell tower becomes a sensing node, the spatial coverage of network-mediated sensing expands from specific installed camera locations to essentially the entire coverage area of the cellular network, which in most developed markets approaches universal outdoor coverage and substantial indoor coverage. That scale shift is what makes the conversation worth having now, rather than later. Let me balance this with some honest limits. Radar-based sensing has physical constraints that prevent it from being the all-seeing eye that alarmist framing sometimes imply. Radio frequency reflections degrade with distance, with indoor obstruction, and with weather. Identifying specific individuals through ISAC alone is extraordinarily difficult. The reflections carry information about physical characteristics, not identity. Connecting a radar track to a specific person requires cross-referencing with other data sources, typically a registered device like a phone, at which point the sensing is no longer without a phone at all. ISAC can detect that a person is present. It has trouble on its own telling the network which person. This is important for calibrating the realistic threat model. The most likely deployment of ISAC in the near term is statistical, population-level sensing of traffic patterns, crowd densities, occupancy counts, rather than individual tracking. Individual tracking through ISAC alone would require significant technical advances beyond the current research frontier and would likely be easier through existing device-based tracking in most scenarios. The scenarios where ISAC becomes genuinely powerful for individual-level surveillance involve combining it with other data streams, device signatures, visual recognition, sensor fusion, at which point ISAC is a component in a system rather than the system itself. What about the claim that 6G is already here? The phrase has a specific, narrow meaning in the context of this conversation. 6G research testbeds are operational. Companies including Nokia, Ericsson, Samsung, Huawei, NTT Docomo, LG, and university consortia have built experimental 6G networks for development and testing. Those testbeds include ISAC capability in various forms. They are not commercial services. They do not cover public areas that ordinary people pass through in the course of their daily lives. They are research installations. Calling them 6G already here is a stretch unless the audience understands the qualifier. The commercial 6G deployment is still several years away, and the specific form that ISAC takes in commercial deployment depends on standards, decisions, and regulatory frameworks that have not been finalized. So the realistic picture is this. 6G with environmental sensing is being engineered. The engineering is at an advanced stage. The standardization is active. The timelines for commercial availability are in the 2028 to 2030 range for early deployments with broader rollout through the 2030s. The sensing capability is real, the privacy implications are real, and the policy conversation is happening now in a window where participation can still shape outcomes. It is not fully here, it is arriving, and the arrival date is not abstract. It is specific enough to plan for. What can an ordinary person do about this? Frankly, at the individual level, not much directly. The defenses against network-side sensing are infrastructural, not personal. You cannot meaningfully shield yourself from a base station's radar reflection when you walk down a street. The defenses have to come from policy, from consent frameworks written into the standards, from data protection laws that treat environmental sensing, data with the same rigor as device-based tracking data, from regulatory oversight that distinguishes legitimate applications from privacy-harmful ones, from technical measures, privacy-preserving signal processing, on-device anonymization, purpose-limited retention, built into the systems at the architecture level rather than bolted on. Individuals can contribute to that conversation. Follow what 3GPP publishes. Pay attention to what your national telecom regulator proposes. Notice what your elected representatives say about AI and connected infrastructure. Support organizations, the Electronic Frontier Foundation, Access Now, European Digital Rights, similar groups in other regions, that participate in the technical standardization and policy work where the actual decisions get made. The more important thing is to update the framework through which you understand cellular networks. The old framework was identity. Who is in the network? The new framework is awareness. What the network can know about the physical world around it. The transition from one to the other is underway. Whether the transition produces infrastructure that serves public interest alongside commercial interest depends on choices being made now, in rooms most of the public has no visibility into. The technology is not the enemy. The technology is an engineering outcome. The question is, what rules the technology will operate under? And that question still has time on it. But not much.